This is about solutions. So this chapter is some new material and some review. So it's a nice way to ease into the second half of that textbook. So a lot less theory, a lot more application. So things like nomenclature, we are not going to go back and rehash nomenclature. The understanding is that you have nomenclature kind of down. So solutions. So just to, having said that, we're going to do just a little bit of review here for a second. And what we're going to cover today, so there's going to be 4 pre-recorded lectures for this chapter. What we're covering today is we're going to review sort of what is the solution. We're going to review energy kind of broadly. We're going to talk about enthalpy. We're going to introduce a new energy term, and we're going to go back and review intermolecular forces. Those were from chapter 11. And then we're going to understand how all these things play together to make up a solution. So we're going to cover all that today. So lots of stuff coming. All right, I'm a very visual writer, so we are going to do some of this. We're going to bounce between slides and my doc cam here, kind of work through the material that way. So just to back up a little bit, if you remember way back when in early days of chemistry, we talked about matter. And matter is anything that occupies space and has mass. And so that's our definition of density, right? Mass over volume. And so matter we can classify in 2 different ways. One was a pure substance, and the other one was a mixture, if you remember. And pure substances, remember, pure substance can be an element, as in like copper or nitrogen or oxygen. It can be a molecule, all your diatomics, and it can be a compound. So all those would be pure substances. So an element would just be like copper, metal. A molecule might be O2, and a compound might be water, carbon dioxide. Those are all considered pure substances. A mixture is one or more substances that are physically mixed together. So the difference between a mixture and, say, a compound, for instance, a compound, they're chemically bonded together. In a mixture, they're just physically mixed together. And so in a mixture, what can happen is you can actually physically separate them. Either you boil off water or you filter, things like that. So a mixture can be physically separated. A compound has to be chemically separated through a chemical reaction. And there's 2 types of mixtures. There's a homogeneous mixture and a heterogeneous. And a homogeneous has a uniform consistency. So if I were to look at a homogeneous mixture, it would look uniform. If I sampled the top of a mixture and the bottom of a mixture, their composition would be roughly the same because it has this uniform consistency. A heterogeneous mixture has a non-uniform consistency. And so you can actually usually physically see all the components because they're not mixed together in a uniform manner. A homogeneous mixture, we have another name for this because we use these an awful lot in chemistry. We call these solutions. So a solution is a homogeneous mixture. If we look at solutions, so there's 2 components of a solution. There's the solute and the solvent. The solute is the minority. It's what's in the least amount, the minority component of that solution. So solute might be sodium chloride, table salt. When you add it to water, where there's a lot more water than there is sodium chloride, the water is going to be your solvent because that's your majority component. Because solutes are the minority component, often your solutions are named after them. Solutions are described by the solute, and the concentration is defined by how much solute versus total solution. And we'll come back to concentrations. But the solute's important because 1, that's how we name it, and 2, that's also how we talk about how concentrated that solution might be. So we go back to the slides here. This would be an example of a solution. But here in this solution, I have water molecules, but I have carbon dioxide gas. And so a solution doesn't necessarily have to be liquid-liquid, solid-solid. You can have liquid with a gas in it. When we carbonate liquids, that's what happens. So here's all the different kind of combinations that we can have. So you can have a gas solution, and these are just a mixture of gases, right? You can have a liquid solution, where I have two liquids that have mixed together, a solid in a liquid. So this might be where I take salt and drop it into and dissolve it in water. I can have a gas in a liquid, like I'm carbonating a liquid, and also a solid. And this is like your alloys, when you have two or more metals that are mixed together. If we look at solubility of a mixture is important. And so you guys learned the solubility guidelines that dealt with ionic compounds. We're going to look at solubility across the board, not just for aqueous solutions. So solubility. In solubility, one of the premises here in solubility is, will a solute be solvated by the solvent? So will it go in solution? That's going to be our solubility. There's a general rule, like dissolves like, if you've heard this. And so that means if I have a solute and a solvent, let's say, my like would be, if this is polar, this is going to be polar. And then those have the ability to be solvated by each other. If I have a non-polar solute, then I would want a non-polar solvent. So I'm not going to take a non-polar solute and try to get that to go into solution with a polar solvent. And I'm also equally not going to take a polar solute and try to get that into solution in a non-polar solvent. And so you're really looking at, when you're thinking about making solutions, you want to make sure that you kind of follow this general rule, likes, dissolves, likes, and then go from there. So we'll build on that, right? So just because I have a polar solute and a polar solvent doesn't necessarily mean that it will go into solution, but it will definitely go into solution over a polar solute, non-polar solvent. Okay, so first rule is I want to make sure that I have my likes, dissolves, likes, and then I'm going to look at what's happening behind the scenes to figure out if something is going to go into solution or not. So before we kind of talk about that, let's review energy. So energy, there's two main types. There's potential energy, PE, and there's kinetic energy, KE. So potential energy, this is energy that's driven from the chemical composition of something. So like TNT has a high potential energy because when that goes into a chemical reaction, a combustion reaction, that's going to generate a whole lot of heat. And so that has a high potential energy. Kinetic energy is more the energy associated with movement. So as things move around, they're going to have a high kinetic energy. Also, potential energy could be where something is located in space, meaning not outer space, but in space, meaning that if I had a rock on the side of a mountain, that has a much higher potential energy than a rock that's at the bottom of the mountain. For chemistry, we're really concerned with, obviously, chemical composition. If we remember back to when we looked at chemical reactions, and we spent quite a bit of time in the thermochemistry chapter looking at chemical reactions and the energy transfer that happens as a result of a chemical reaction. And we said we could define the change in internal energy of the system as Q plus W, where Q is heat, this is heat, and this is work. And then we further went in and said, okay, if I'm looking at a chemical reaction and I have that reaction occurring in a scenario where I have constant pressure, so I have Q at constant pressure, then this whole term becomes delta H, which is enthalpy. So this is the heat of the reaction at constant pressure, heat. And so if I look at delta H of the reaction, we said that the sign of delta H can tell you which direction that energy is going. Is the energy being absorbed into the chemical reaction, or is that chemical reaction releasing energy? And here we're thinking about heat, right? QP, heat, so we're looking at really thermal energy. And we said if delta H of the reaction, and this is kind of all review from that chapter, if it's positive, then that means my chemical reaction is endothermic. It absorbed energy from the universe or the surroundings, right? So that means its energy increased as a function of that chemical reaction. If delta H of the reaction is negative, then that's exothermic, and energy was released as a result of the reaction. So when this happens, when I have an exothermic reaction, my products have a lower potential energy than my reactants because energy has left that system. Conversely, up here for a positive value in endothermic, now my products have a higher energy than the reactants because the whole thing has absorbed energy. Energy has gone into that system. So we can also apply this idea of energy transfer to a solution. Even though we're not physically conducting a chemical reaction, we're physically mixing substances together, I can still have this energy transfer. I can still have a heat transfer. If I mix two things together and it starts to get warm, that's going to tell me that energy is being released, thermal energy is being released, and the delta H of that solution, now I'm going to call it a solution instead of a reaction, is going to be negative. If it gets colder, then the delta H of that solution is positive and it's endothermic, meaning it's absorbing heat from the atmosphere. So just as we applied this to a chemical reaction, we can also apply it to a solution. If we have that in the back of our mind and we think about the driving force of a chemical reaction is to lower its potential energy, then if we have a solution where we lower the potential energy of that solution, then that should favor the formation of that solution. We're going to come back to enthalpy in a second, and we're going to kind of take an offshoot here and talk about another energy term. So enthalpy is H, and that's the heat of a reaction. We'll also call it the heat of solution. So delta H SOLN would be the change in heat of the solution. So what's happening in that when I make that solution, is there a transfer of heat there? This is going to deal with heat as energy, right? My thermal energy. My other term is entropy. And entropy is S. And entropy is a measure, it's not heat, measure of disorder, dispersal. So if I allow things to disperse more movement, more freedom of movement, all that is entropy. And if by forming a solution, think about a solid. If I take a solid and I drop it into water, whether it's a covalent compound or an ionic compound, what's going to happen is those molecules that are in that solid are going to move apart, and now they're going to be able to flow with the water. And so by forming a solution, I'm increasing the entropy. So this will always be favored in the formation of a solution. It's not changing potential energy or kinetic energy. It's a different form of energy altogether. So enthalpy, remember, is heat, and that's how we traditionally think of energy. But entropy is also an energy term that's less that you can touch and feel and more kind of a theoretical concept. When you think about gases and what's happening with a gas, gases are a very typical representation of what might happen in a solution that's being formed, because gases don't have a change in potential energy. So if I take a sample of neon gas and a sample of argon gas and I have them separated and I remove the separation, they're going to spontaneously, without any interference on my part, mix together and form a solution. That solution has the same energy in terms of potential energy, but something has allowed those gases to mix. There's another energy term there that's favoring that, and that's entropy. And we're not going to spend a lot of time on entropy in this chapter. We're going to come back to it when we get into thermochemistry, but just to say that there are two things that are going to affect whether a solution will form. One of them is enthalpy, which we'll come back to in a second. The other one is entropy, and entropy always favors the formation of a reaction because you're always increasing the disorder, increasing the movement of those molecules. Enthalpy, however, may or may not favor the formation of a solution. So entropy it has a spontaneous drive to spread out. So the more freedom you give something, the more ability you allow it to increase movement, to disperse. That's always going to be favored from an entropy. Enthalpy is very different. So enthalpy, let's come back to enthalpy. So the only thing I kind of want you to take away from for entropy is that solutions that appear to be unfavored from an enthalpy standpoint may still occur because entropy is favoring them. So you have two things that are going on. Enthalpy, big H. Remember, this is a state function. We're often looking at the change in enthalpy, and now we're going to apply it to a solution. So this is going to be called the heat of the solution rather than the heat of the reaction. This is going to be in units of kilojoules per mole, just like before. But now, instead of looking at a chemical reaction, we're going to look at the formation of the solution. So heat of a solution, the formation of a solution. And like before, the sign of delta H is going to tell me where the energy is going. So the sign is going to be important. All right, so enthalpy may or may not favor whether a chemical solution will form. And so what is going on in the solution where we would need to consider the enthalpy? And so we're going to back up here and talk a little bit about intermolecular forces, IMFs. This was from chapter 11. And so chapter 11, we had, these are going to be these forces that are between molecules. So in a compound, when you form chemical bonds, those are forces within a molecule. These are going to be forces between molecules. Between, anytime you see inter, that means between. So if I have an interstate, it's between the states. That freeway is going to go across many states. So intermolecular forces happen between molecules. Now remember from gases that gases, the tenet that we can treat gases as ideal, gases have no intermolecular forces because they have high kinetic energy, they're in constant movement, they're always moving, and so they really don't have any intermolecular forces between them. So when we think about intermolecular forces, we're thinking about liquids and solids, because in these cases the molecules are closer together and they're connected, not bonded, but connected by these intermolecular forces. They're holding them together. They're not bonding them together, but they're holding them together. So the stronger the force, the stronger the intermolecular force, the less movement, and the stronger the connection. I almost said bond between molecules. So solids have stronger intermolecular forces than liquids. That's what makes them solids, right? So you're constricting the movement. So a solid is greater than a liquid, which is much greater than a gas, because a gas has no intermolecular forces to begin with. And just to review what those intermolecular forces are, and like I said, this is from chapter 11. So if you're a little rusty on it, you might want to go back and just kind of look again at these types of intermolecular forces. So the lowest energy intermolecular force is a dispersion force. And this is an instantaneous, they call these instantaneous dipoles because it's a force that happens between molecules. You have a shifting of electron density, which creates a transient, instantaneous, non-permanent dipole that happens, and then if there's another molecule near there, it will force that molecule to have an instantaneous dipole. And so these are very fleeting. They don't last very long. But the thing with dispersion forces is they can be additive. So if you have a really long molecule, you can have like thousands of these dispersion forces happening between two molecules if they're really long. And those forces can start to add up even though they're really, really small. So my favorite example of dispersion force is a lizard, so geckos in particular. And so geckos can kind of run up walls, and it's not because they suction onto the walls, which is, I guess, used to be a thought, but because they have these intermolecular forces, specifically dispersion forces, and they have hundreds of thousands of them that are happening between the pad of the lizard that has these little thin little hair-like substances that come out, and whatever the surface is that it's on. And so holding that lizard on are these really very small dispersion forces, but there's millions of them. So they're very additive. So that's the lowest type of intermolecular force. So in order for a solid or a liquid to form a solution, you have to break the force that's holding those molecules together. So if it's a dispersion force, I have a lower energy barrier to overcome. As I have more and more of a dipole moment, that force is going to get stronger and stronger and stronger. And so a dipole-dipole intermolecular force is between two polar molecules. And remember, in a polar molecule, you have a partial positive and a partial negative end of those molecules. And so this force is happening between them. Hydrogen bonding is a specific type of dipole-dipole where it's kind of misnamed because it's not a bond. It's still this intermolecular force, but it happens between molecules where hydrogen is bound to a highly electronegative element, oxygen, nitrogen, and fluorine. And so you have to have hydrogen bound to oxygen, nitrogen, or fluorine, and then you have this association between the hydrogen in one molecule and the electronegative element in the other. And that's a hydrogen bond. It's much stronger than a dipole-dipole. And then at the pinnacle of this, or the highest, is ion dipole. And this is where you have aqueous ionic compounds. So this is the intermolecular force that forms that allows an ionic solid to be broken apart and be solvated. So these are intermolecular forces. These are the forces that are going to have to overcome to form a solution, and then these are the forces, the favorable forces that you gain when you form a solution. And so when we think about enthalpy, now we're going to look at these intermolecular forces and see how much energy we have to put in to break the intermolecular forces that are happening with the solute and the solvent, and then the force, the energy we get out when we form new intermolecular forces between the solute and the solvent. So that's where we're going to stop right now. So we did a lot of review all the way through to intermolecular forces in your textbook. So in part 2, we'll pick up and we'll talk about heats of solutions and specifically looking at these different types of forces that we have to overcome.